Today, we're going to review our trigonometric substitution and do an example and possibly look at an example of not trigonometric substitution that looks like it might be trigonometric substitution. So let's take a look at an example. I'm just going to use a classic example. Let's suppose that we have the integral of the square roots of, let's go with 25 minus 9x squared to x. What should call to mind trigonometric substitution is we're trying to integrate a function with a quadratic, usually a quadratic with a square root, a quadratic with a 1/2 power, either in the numerator or in the denominator. We're looking for quadratics. The quadratics don't have to be factorable. They can be factorable, like 25 minus 9x squared is 5 minus 3x times 5 plus 3x. But we would do the same. We would also think of trigonometric substitution if we were looking at 25 plus 9x squared. That would just be the tangent case. The idea is to trade our integral in x for an integral in theta. The reason that we're going to do this is that we have this quadratic, which is 2 terms under a radical, and that's messy. We don't like that. I'd rather have 1 term under a radical because then we have ways out of that. So we do the trigonometric substitution to get into an integral in theta that will be a product of powers of trig functions. And like we discussed before, we'll be looking at even powers of cosine or odd powers of secant. Otherwise, there were probably something we could have done in the original integral to avoid trigonometric substitution in the first place. So we do the trigonometric substitution, we get our even powers of cosine or our odd powers of secant, and we have ways of integrating even powers of cosine and odd powers of secant. That gets us to an antiderivative in theta. And then the final thing that we have to do is get out of theta and back to x. And that was the triangle thing. That's Act 3, that's the triangle thing. It's a little bit more involved than just replacing the w with what you substituted at the beginning, because we're going to be making a substitution x equals some trig function of theta, and it's not as easy to get out of that as it was to get into that. Any questions? Then let's begin. So we look at, we see this integral, and we recognize it as the sine case because it's an a squared minus x squared. That's the sine case. We have to know what we're going to substitute. So what we notice is that we have a coefficient in front of the x squared. So one of the things that we might do is to factor out the coefficient of x squared so that we can see what our trigonometric substitution should be. Maybe we don't see it as see it right away. So let's do a little algebra on this. I'm going to factor out a 9 from the inside this from the 25 minus 9x squared, and that'll give me a 25 over 9 minus x squared. So that tells me what my trigonometric substitution should be. And that tells me that trigonometric substitution, x should be 5/3 sine of theta. We've identified what a is, so now we can say that x should be 5/3 sine theta. If x is going to be 5/3 times the sine of theta, then dx will get replaced with 5/3 cosine theta d theta. And we know that we're going to have to use a Pythagorean identity. We know we're going to have to replace a 1 minus sine squared theta with cosine squared theta. The reason that we're doing this is to get at the Pythagorean identity so two terms can become one term. This is the trigonometric substitution Thunderdome. Two terms enter, one term leaves. In the example we did last time, I left this 9 factored out, but we don't have to. The reason that we factor out the 9 is so we can see what the coefficient of the trig function should be. But we can just take this x and substitute it back into the original. So let's take a look at what will happen. We have the integral of the square root of 25 minus, and then, oops, I forgot to write 9. That was a half save. And then the x gets replaced with 5/3 sine of theta squared. That's only part of the substitution. We also have to substitute the dx, and that's going to be a 5/3 cosine theta d theta. Now the thing happens. Now we go on to the two terms become one term. So this is going to become 25 minus 9 times 5/3 sine theta squared. That was just spelling it, sorry. It's going to be 25, alternate color, 25 minus 9 times 25 over 9 sine squared theta. And so this is going to be 25, since the 9's cancel, this is going to be 25 minus 25 sine squared theta. We can take out the 25 and leave 1 minus sine squared theta. And so this is all going to become 25 times cosine squared theta. Just hit it with the algebra hammer for a little while. Two terms become one term. That was the thing that we wanted to happen. That was the goal of this process. So this is all under a radical. Let me clean all this up without simplifying the integral parts. We have the square roots of 25 cosine squared theta. And then we have this all multiplied by 5/3 cosine of theta d theta. This is where we wanted to be. The square root of 25 cosine squared, we can simplify that to just 5 cosine of theta. I still have this 5/3. I'm going to pull my constants out in front because I always do, and we'll have 25/3 times the integral of cosine squared theta d theta. This is where we're at the g of theta part. This is the end of Act 1. So we have done that first step. We have gone from our integral in x to an integral in theta. And as is the case with trigonometric substitution, we have ended up with a product of powers of trig functions. And we ended up in this case with even powers of cosine. Remember that we integrated cosine squared by parts. That is not how we normally integrate cosine squared. We did that because there was something to be learned from that process. How we actually integrate cosine squared is to use a double angle identity, because integrating cosine squared is just a trig identity away from integrating the cosine of 2 theta, which is preferred. So we replace the cosine squared. Now we're going to start Act 2. we're going to replace the cosine squared with a half plus a half cosine of 2 theta. This is not the integral of cosine squared. We're not integrating cosine squared to get 1/2 plus a half cosine theta. We're just replacing the cosine squared with a half plus a half cosine of 2 theta. So we're still looking at the 25/3, and we're still integrating, but now we're going to integrate 1/2 plus 1/2 cosine of 2 theta. The reason that we make this replacement is that integrating a half plus a half cosine of 2 theta is much easier than doing parts on cosine squared or some other shenanigans on a cosine squared. So now I'm not going to write an integral symbol because I'm integrating the 1/2 plus a half cosine of 2 theta. So it's going to be a 1/2 theta and a 1/4 sine of 2 theta. Oops, derivative of sine is cosine, so integral of cosine is sine. So I got a 1/2 theta plus a 1/4 sine of 2 theta. The 1/2 from the 1/2, the 1/4 because we have to divide by the coefficient of theta. Here we are at the end of Act 2. We've done the integration parts. This is our antiderivative in theta. Oops. We have now gone across, we've done our integration. We now have an antiderivative in theta. That's the end of Act 2. The last thing that we have to do is get back to x. This is Act 3. This is the triangle thing. Any questions?
Professor, to get the 1/4, you just did integration by parts?
Mm-mm. The integral of cosine of 2 theta is 1/2 sine of 2 theta, and then I had to multiply by a half.
Okay.
So this part right here, the integral of cosine of 2 theta d theta is a 1/2 sine of 2 theta.
Okay.
And then I multiply 1/2 sine of 2 theta by 1/2 to get a 1/4.
Got it. Okay, thank you.
All right, so now we have an antiderivative in theta. The last thing that we have to do is go back to x, go from our antiderivative in theta to an antiderivative in x. We also need to flip pages. So what we have is our antiderivative in theta, which was, actually, I'm just going to repeat this step. 25/3, and then we had a 1/2 theta plus a 1/4 sine of 2 theta plus c. So if we want to clean, we can clean this up a little bit and say this is 25/6, no, 25/6 theta plus 25/12 sine of 2 theta plus c. Here's our antiderivative in theta. Now we need to go from theta back to the x. What we have in evidence is that x is 5/3 sine of theta. So we're going to start replacing pieces. So if x is 5/3 sine of theta, then I can write sine of theta as 3x over 5, or 3/5 x. So that's one piece that we can replace. I can say that sine of theta is 3/5 x. I also need to replace a theta. So I can say that theta, oops, actually from here, theta is sine inverse of 3/5 x. So I can replace the theta with sine inverse of 3/5 x, and I can replace the sine of, oh no, it's the sine of 2 theta, and I have the sine of theta. Fortunately, these are trig functions, and there's an identity for that. So we also know that the sine of 2 theta is 2 sine theta cosine theta. So there's just like always with trig functions, there's a trig function for that. Or sorry, there's a trig identity for that. So now we can just replace the sine of 2 theta with 2 sine theta cosine theta. And I can replace the sine theta with 3/5 x, but oh, now I need a cosine theta. So I'm going to draw a right triangle. To help me remember where things are going to go. I'm going to read the sine of theta as 3x over 5, where 3x is the opposite and 5 is the hypotenuse. So if I put the hypotenuse in the hypotenuse spot and 3x opposite, then I can solve for the adjacent side. The adjacent side is, unsurprisingly, the thing that led us into trigonometric substitution in the first place. Using the Pythagorean theorem, if 3x is opposite and 5 is hypotenuse, then the adjacent side is 25 minus 9x, the square root of 25 minus 9x squared. So now I'll be able to replace the cosine of theta with adjacent over hypotenuse. So I've got 25/6 theta. I've got 25 over 6 times theta, and theta is sine inverse of 3/5 x. I'm going to have plus 25 over 12 times the sine of 2 theta, which I'm going to replace with 2 sine theta cosine theta. Still haven't lost my constant of integration. So I'm going to replace the sine theta with 3x over 5, and I'll replace cosine theta with the square root of 25 minus 9x squared over 5. So I still got this term. Let's see, I can dump a 2. So I have 25 over 6. Sine of theta is 3x over 5. Sine of theta is 3x over 5. And cosine of theta is the square root of 25 minus 9x squared over 5. And then we still have a plus c. And we still have a cleanup on aisle answer. Here we can dump a 3 and a 6 with the 6 and then the 2 5s. So our final answer is 25 over 6 sine inverse of 3/5 x plus 5's cancel, and the 3/6 is 1/2 x times the square roots of 25 minus 9x squared plus c. And that is my final answer, Regis. They never have like calculus on quiz shows like that. All these people walking around thinking they know lots of stuff. Meanwhile, in Jeopardy, you never see the category. And our final category and our final Jeopardy category is calculus. Any questions? So this seems like a lot to remember, but that's only because this is a lot to remember. We can break it up into 3 parts. And the first stage is just recognizing what those 3 parts are. And recognizing when you've reached the end of each of those 3 acts. On top of that, you have to recognize when you should do trigonometric substitution. So you're trying to decide, so the first thing is, how do we decide when to do trigonometric substitution? Trigonometric substitution is for when we have a quadratic in the square, and usually a quadratic under a square root. And there are 3 cases of trigonometric substitution based on what kind of quadratic we have. So there are 3 cases of trigonometric substitution. There's the sine case, where we have something of the form a squared minus x squared. That's the form that we had here. A squared minus x squared. There's the tangent case, where we have the form a squared plus x squared. And then there's the secant case, where we have x squared minus a squared. And those are our substitutions.
So we don't have one for like cosine.
What's that?
So we don't have one for cosine specifically.
We don't need one for cosine because we've got one for sine.
Gotcha.
Remember, the goal is to use 1 minus sine squared theta is cosine squared theta. And remember, the other thing that goes along with this is that dx is going to be a cosine theta d theta. We could reframe the sine case as the cosine case, but then the dx will be -1 times a sine theta to theta. It would work just fine. It would do the exact same thing that we wanted to do. But we'd end up having to integrate sine squareds, and when we want to integrate even powers of sines, we turn them into even powers of cosines. So we take the direct route, call it the sine case, and turn everything into cosines. See, I told you at the beginning, this would all make sense. It would just be a lot to remember. Like I said, it only seems like it's a lot to remember because it's a lot to remember. And you have to remember all of it all the time in perfect detail. So I don't know what you're all complaining about. So there are two questions that we have that could be raised at this point. Two concerns that we could bring up if we weren't so distracted by all the tons of details that we have to remember. But let me point out two concerns. I know you probably have way more than two, but one is you said something you might be sitting there thinking, Leach, you said something about not needing to do a trig substitution. Oops. So do we always use trigonometric substitution with quadratics? And the answer is, of course, no. If the answer was yes, I wouldn't be writing this. I would have just said, always do this. Specifically, we got to watch for regular substitutions. Don't forget your regular substitutions. And the second concern, one that we might not have thought of, is what happens if there's an x term? You're talking about these quadratics. What if the quadratic has an x term? Oops. Oh well. So I specifically refer to these quadratics, and then I gave you a squared minus x squared, a squared plus x squared, and x squared minus a squared. But quadratics might have an x term, so there's a legitimate concern. What if there is an x term? And we need to have an answer for that, because that could come up. So, second thing first, what if the quadratic has an x term? If the quadratic has an x term in it, we do what we always do with quadratics with x terms in them. We complete the square. I haven't asked you all to solve a lot of quadratic equations because we've got so much calculus to do. But I fear that for the most part, if I asked you to solve a quadratic equation and I gave you something that wasn't factorable, you'd use the quadratic formula. And that's a great tragedy. I'm not blaming you. We as a math instruction community did that to you. We gave you this quadratic formula. And we said, just do this if you can't factor it. And man, I have to apologize on behalf of the math education community. Even the ones that don't know, they should be apologizing to you for doing this quadratic formula, because the quadratic formula is trash. So let's suppose that we want to integrate, let's say, the square roots of x squared. I'm going to use the one that I always use. Wait, should I? Yeah, 3 squared is 9 and 4 is 13. So this certainly fits the bill of a quadratic in a square root. That's what makes us think trigonometric substitution. That's what's triggering our trigonometric substitution thought. Quadratic, square roots. This looks like a job for trigonometric substitution. But, dude, there's this x term in there. So we just get rid of this x term. We take these 3 terms and make 2 terms out of it. we just rewrite this as x squared minus 6x plus 9 plus 4. We break up the 13. We use a 9 to complete the square and write this as an x minus 3 squared plus 4. Now we can see that this should be the tangent case because there's an x squared plus an a squared. But instead of saying x equals 2 tangent theta, we substitute whatever's being squared. X minus 3 is going to be 2 tangent theta. Everything else proceeds as normal until we get to Act 3, when we might have to solve for the tangent. We just make sure that we have an x minus 3 as in tangent as the opposite. So notice that if we take the derivative through here, then dx, the derivative of the 3 is 0. The dx is still 2 secant squared theta d theta. And once we're in trig functions, once everything's in terms of theta, then we're still going to say that tangent squared plus 1 is equal to secant squared. Any questions? On a side note, in the category of so many things to remember, I want to admit to you right now that I have difficulty remembering the relationship between secant squared and tangent squared. But I never have a problem with this. I only have a problem with this in trig class because I can't remember it. I never have a problem with it in calculus class because I recognize this as the tangent case, and I remember the point of doing this process is to replace tangent squared plus 1 with secant squared. That's what told me what to write down here, not my memory. I can't rely on my memory for things like tangent squared plus 1 equals secant squared. The only Pythagorean identity I can rely on my memory for is sine squared plus cosine squared is 1. That's a lie. I always write it cosine squared plus sine squared equals 1. That's as far as I can go. But I don't have to remember the relationship between secant squared and tangent squared because I remember what I'm doing. I don't separate this out into a separate thing in my mind. I remember the point of doing trigonometric substitution is to combine these two terms into one term. And I remember that it's the Pythagorean identity that gets me there. That's how we start putting things together. We stop compartmentalizing all these things to remember, and we start putting them together. The more connections we make between these things, the easier it is to remember because we have more ways to remember the thing that we're trying to remember. So then the problem becomes, once I've rewritten this as x minus 3 squared plus 4, I'm not going to do this whole problem. Then the x minus 3 gets replaced by the 2 tangent theta. And the dx still gets replaced with 2 secant squared theta. Two tangent squared theta plus 4 becomes 4 secant squared theta. And then we just have even powers of secants. Oh, sorry, odd powers of secants. Now, the other place that this unusual substitution is going to show up is at the end. So this is going to be the integral of let's see, square root of 4 secant squared theta. I can put the 2's together and have a 4 out front. And then I have secant, the square root of secant squared is secant times secant squared is going to be a secant cubed. Yikes. So I'll pull the 4, integral of secant cubed theta d theta. That's the end of Act 1. So this is going to give us an expression with a bunch of secants and tangents in it. So if we have x minus 3 is equal to 2 tangent theta, then solving for tangent tells us that tangent of theta is x minus 3 over 2. And so that's going to be the opposite and the adjacent. In the right triangle, with an x minus 3 opposite and a 2 adjacent, we need to solve for the hypotenuse. The hypotenuse is going to be the square root of x minus 3 squared plus 4. Because the third side that you're looking for in this triangle is always going to be the thing that told you to do trigonometric substitution in the first place. This is just going to be the square roots of x minus 3 squared plus 4, which if we multiply that out will be x squared minus 6x plus 13. The third side in your triangle in Act 3 is always the thing that triggered the trigonometric substitution in the first place. So then we could use this to write secant theta which is hypotenuse over adjacent. And we take the hypotenuse roots x squared minus 6x plus 13 over the adjacent side, which is 2. This one does theta, but we could just do theta is tangent inverse of x minus 3 over 2. We don't need that in this. We won't need that in this case. All right, we ran a little bit over time, but that was a lot of work. Trigonometric substitution is a lot of work, and that's why most people don't like it. Yeah, that's kind of it. That's kind of the end of that sentence. Most students don't like it. But let me tell you, the reason that you don't like it is it because it calls on you to remember a lot of things that you don't necessarily remember right away. But by practicing trigonometric substitution, you'll start to remember those things and more connections will be made. Doing these problems is going to help you remember the things in trigonometry that you forgot. And I assure you, there are things in trigonometry that you forgot. And by forgot means, I mean, you were in a trigonometry class, you got to things like double angle identities, and you just didn't spend time on those. And then you show up in my calculus class, and I go, hey, remember double angle identities? And you're like, oh, no. And I'm like, oh, good. Glad you all remember your trigonometric identities. And you're like, oh, wait, no, and then we just go on. Any questions? Comments? Snide remarks? All right. Sorry we went a little overtime today, but that'll do it for today. I will see y'all on tomorrow where we address our other concern. That is, don't forget your regular substitutions. I'll see you all on tomorrow.
That's it for today. Everybody have a good day, and thanks for playing.